Cosmic rays are part of the natural radiation we are exposed to and are everywhere. Hundreds of particles from cosmic ray caused air showers pass through your body every minute, and scientists are still trying to figure out how many ways they influence our lives. So, what are cosmic rays? They are high energy subatomic particles made in stars, supernovas, and other processes. When cosmic rays enter our atmosphere, they interact with nitrogen or oxygen atoms, convert their energy into mass, and cause an air shower of less energetic secondary cosmic rays. Most of the particles produced quickly decay into other particles, but the most common particle it decays into is a fundamental particle called a muon that reaches the Earth's surface. To detect these muons, I used plastic panels that are doped with a special chemical that causes it to emit photons of light when a muon passes through the panel. Because the light emitted is too weak to be properly detected, it is drawn into the photomultiplier tube shown here and amplified so that it can be detected. The amplified signal is sent to a data acquisition board, which collects and sorts the data with timestamps. Cosmic ray detectors can be used in several experiments that can tell us interesting facts about cosmic rays. The first experiment I did was finding the speed of muons. Measuring the speed of muons is just like those rubber hoses that the city uses to measure traffic on the road. It takes a timestamp when the first hose is driven over and when the last hose is driven over and measures the difference. It divides the difference by the distance between the two to get the speed, so we need at least two panels. As it turns out, muons are very fast. How fast? About 99.7% the speed of light, or about 300,000 kilometers per second. Because they were so fast, the detectors needed to be a certain distance apart, or the muons would pass through them at roughly the same time, and I wouldn't be able to get an accurate timestamp. Similar to how, if the hoses were too close, the car would drive over both at about the same time. But once spaced out enough, the results matched with what other people had gotten. The high speeds that muons travel at also allows them to reach the Earth's surface before they decay, as they have a lifetime of just 2.2 microseconds. As previously explained, air showers are caused when cosmic rays enter the atmosphere, convert their energy into mass, and produce a spray of secondary cosmic rays. The more energy a cosmic ray has, the more mass it produces when entering the atmosphere, and the larger the air shower is. We can detect these air showers by laying the panels on the floor a certain distance apart from one another. If a muon passes through each panel at the same time, that means that the muons came from the same air shower. The greater the distance between the three panels, the larger an air shower has to be detected, and the more energetic the cosmic ray has to be to cause the air shower. Cosmic rays have a wide range of energies, but their flow decreases sharply as higher energy levels are reached. This matches up with the data I gathered, as shown on screen. Some cosmic rays are so energetic that we don't know of a process powerful enough to create them. As stars are one of the sources of cosmic rays and the Sun is the closest star to Earth, it would seem reasonable that the detectors facing away or towards the Sun, as determined by the time of day, would have an important impact on how many secondary cosmic rays are detected. To see what difference time of day made, I ran the detectors for 3 days and set them to only record muons that passed through all of the detectors within a certain time interval. My hypothesis was that because the Sun was a source of cosmic rays, there would be fewer muons detected during the night because of the Earth between the Sun and the detectors. After gathering 3 days of data, I saw that there was no consistent relationship between the number of muons that were detected and the time of day, which was exactly what other people had found. Though the Sun is a source of cosmic rays, there are so many more powerful sources out there, and the Sun's cosmic rays were relatively weak compared to most of them, that any difference due to not facing the Sun was insignificant and offset by receiving other cosmic rays from a different direction. Despite what humans have already discovered about cosmic rays, there are still plenty of things about them that we don't know. As mentioned previously, some ultra-high cosmic rays would have to be made by processes more powerful than anything we know of, and discovering its origin is one of the bigger problems in astrophysics right now. Scientists are trying to figure out how to find any cosmic ray's origin by looking at what they are made of. 90% of cosmic rays are made out of hydrogen nuclei, and another 9% are made out of helium nuclei, both of which are very abundant in the universe, but the remaining cosmic rays are all rarer elements that the scientists can look for. They also use how long it takes for the cosmic rays to decay to estimate how long the cosmic ray has been traveling through space for before reaching Earth, which can narrow potential origin points down. Just these questions alone will probably be active for a long time.